Hi, this is Kevin. Welcome to my lecture on Chapter 3 of the Zelle 3rd edition Python programming book. Chapter 3 is about computing with numbers. The objectives I'm going to leave for you to read on your own. So when we work with numbers in Python, we need to create number objects. And all of the programming objects in Python are based on a type system. So what we're interested in here is which of the data types are numeric that we want to use and talk about in this chapter, and what are their characteristics. Okay, so there are two different kinds of numbers that we're interested in. We have whole numbers like 5, 4, 3, and 6. They don't have a fractional part, and we have a data type for them. And then we have decimal fractions, things that come after the decimal point, like 0.25, 0.10, 0.05, 0.01, and we need a number type for them. So inside the computers, whole numbers and decimal fractions are represented quite differently. So we need two different data types. Okay. And the data type of a value object determines what values it can have and what operations can be performed on it. Whole numbers are represented using the integer data type. We call it int for short. So the name of the type is int. These values can be positive, 0, or negative, whole numbers. Numbers that can have fractional parts, that can have a whole number part and a decimal fractional part, are represented as floating point, or as the type is called in Python, just float. How can we tell which is with? Well, if we're typing in a literal value in our code, if we type in a literal value without a decimal point, then that becomes an int value, like 1 or 5 or 0. If we type in a literal value in our code in some expression and it includes a decimal point, then it's going to be represented as a float. So 1.0, 5.0, 3.9, 125.333, all will be represented as a float. Python has a special function that we can call to see what type any value is. And here you can see that they're working in the Python console. As I've said in previous lectures, we sometimes call this console the REPL, all caps REPL, read, evaluate, print loop. And this isn't typically the way that we write or run programs, but it's a great way to experiment when we're learning. So if we ask for the type of the literal value 3, well, it's an int. The type of the literal value 3.1 is a float. Okay? Interesting, you can see that the answer we get back is class int or class float. In Python, all of the type objects are instances of a particular Python class. So the integer or int type is implemented with the int class, and the float or float type is implemented with the float class. Okay? Why do we need two types for numbers? Well, it's pretty practical, and we'll be getting to it in just a second. So, values that represent counts of things typically can't be fractional. Okay. Now, there are some things. Uh, I guess this is a semantic kind of a difference, but typically we use the word count when things are in whole units that can't be divided, right? So, for instance, you can't have 3.5 quarters, quarter as in the American coin. Um, well, you could. I mean, you could saw a coin in half, but then it wouldn't be valid currency anymore. So maybe if we have a count, we want to use an int type. Now, most mathematical algorithms are very efficient with integers. So one of the reasons that we like to use int types whenever it's appropriate is that the computation on ints is faster than the computation on floats. Okay. The float type stores only an approximation of the real number being represented. Since floats aren't exact, use int whenever possible. So if we have a value that we're keeping that is always going to be in whole units, well, let's represent it with an int, okay? It's going to be less troublesome in terms of approximation errors, and it's also going to lead to faster computation when we use it in formulas. Okay. Now, generally speaking, if we have int values and we are performing some kind of mathematical operations on it, we're going to get ints. Okay, and generally speaking, if we have float values and we perform some mathematical operation on them, we get floats. There's an exception for division. Okay, so down here we see some experimental work in the Python console. So 3.0 and 4.0 are floats, and when we add them, we get 7. 3 plus 4 are ints. Oh, sorry, when we add the floats, we get 7.0, so we get a float. When we add the ints, we get 7. That's an int. If we multiply two floats, we get a float. If we multiply two ints, we get an int. Now, if we divide a float by a float, we get a float. Okay? The slash operator is a float division. Okay? Now, there's a slash operator that does integer division. Okay? So, 10 divided by 3 will give us a float. Why? Well, the two operands were ints, that was fine, but the slash is a float division operator, so it's going to give us 3.33333, etc. If we do 10 slash 3, we're going to get a 3. So this is a kind of basic early arithmetic division where we get a whole number answer and a remainder. Okay. So we've only asked for the whole number answer, so we get a 3, an int 3. If we use an integer division operator between two floats, like 10.0 / 3.0, we get the integer answer expressed as a float. So we throw off the fractional part because using the slash says, I want to do integer style division, okay? But because we use floats, it goes, oh, and then I want to convert it back to a float. So we've lost that 333333, but we have a float answer. Now, what the use case is for this, I'm not exactly seeing at this point, but we can make it happen. So integer division produces a whole number. That's why 10//3 equals 3. Now, I want to point that this exclamation point is not part of the code, it's part of the slide. Okay, so it doesn't equal 3 exclamation, it equals just 3. Think of it as it goes into where 10//3 equals 3, since 3 it goes into 10 3 times with a remainder of 1. So we get the whole number answer and not the remainder. What if we wanted the remainder? Well, we have this other operator that some people call the Modulus Operator, or some people call the Modulo Operator. And what does it give you? It gives you the remainder. So 10 modulo 3 equals 1. That's the remainder. Okay, I just want to point out that here on the slide, we're jamming all this code up against each other without intervening spaces. And that's not because we think that's the right way to format our code. That's because the author of the slide was concerned that he or she was going to run out of room on the slide. Okay. Type conversion and rounding. So we know that combining an int with an int produces an int, and combining a float with a float produces a float. What happens when you mix an int and a float in an expression? So what happens if you have a multiplication between a float 5 and an integer 2? Well, I always hate these. What do you think should happen? You get a float. That's what happens. For Python to evaluate this expression, must either convert the float to an int or the int to a float. Converting a float to an int would lose information. So it converts the int to a float. So if we have a regular expression, not a / expression, okay, because those are different. If we're doing an operation with an int and a float, well, it converts the int to a float, and then it does float arithmetic. Which is why we have a bullet here that says in mixed type expressions, Python will convert ints to floats. Sometimes we want to control the type conversion. This is called explicit typing. Converting to an int simply it discards the fractional part of a float. The value is truncated, not rounded. Now, this is a really important point, and a lot of people miss this, right? If we have a value in a float type, like 5.123, and we convert it by calling the function int. So we say int paren 5.123. What value are you going to get from that? You're going to get just 5. What if it said 5.999? You know, int 5.999. Likewise, you would get only 5. There's no rounding. It truncates the decimal fraction. As long as you know that that's how it works, great. Okay. Now, what if we wanted to round? Okay, there are a lot of times when we want to round. Well, there's another function for that. So if we wanted to convert um, a float value to an int value and make sure that we round it appropriately, well, we would use the function round. So a round of 5.123 is going to give you um, the int value 5. A round of 5.999 is going to give you the int value 6. Okay? So if we just use int, we truncate off the decimal fraction. If we want rounding, we need to use round. Now, what if you wanted to round a float and come up with a float, but just round how many digits of decimal fraction you had? Well, you just use a second parameter on the call to round. Let's see that. Okay, so here we're at the REPL again. So let's see what we've got. Well, we have examples of a lot of things. Okay, a float of 22 slash 5. So 22 slash 5 is going to give us 4. That's a decimal divide. But if we convert it to a float, it's going to be a 4.0. Int of 4.5 is 4. Int of 3.9, it's truncated again, 3. Round of 3.9 is going to be a 4. Round of 3 is going to be a 3. If we want to round 3 point blah, 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 I think this is the pi number, comma, 2 decimal places, then we're going to get 3.14. Now it's 14 because the next of the digits is a 1. Okay, if we, for instance, said we wanted to do this to 1, 2, 3, 4 digits, okay, we would get 3.1416 because the next digit is a 9. Okay. So now we can convert from strings to internal number values. And this is sometimes pretty challenging for new programmers because in our thinking as a kind of lay people going around in the world, okay, the difference between a character 32 and an internal integer type value 32, a string 32 and an int 32, it's not part of our normal thinking. It's not part of our normal life. We see the character string 32 on the page and it gets converted to a conceptual 32 in our head instantaneously. Right? We don't have to think about some conversion that happens. But in the computer, strings are very different than ints. The good thing about a string 32 is that it's easily typed in by a user. The other good thing is it's easily printed out for a user to see. So when we're doing user interface, the user types in string numeric values, okay? And when we print out string numeric values, okay? But once, when we're doing some kind of input, all right, if the user is going to type in a 32, we need to convert it to an int 32 by calling int on it. So you can see this is a string 32 because it's surrounded with quotes, okay? If we want it to be a float, then we call float, and we get 32.0. Now we're going to begin to use this rather than eval, okay? Eval is insecure, Okay. It was very popular because of its flexibility. Um, One of the nice things about eval was if the user typed in a 32 and we evaled that, well, we would get an int 32. If the user typed in 32.0 and we evaled that, we would get a float 32. And that would be kind of nice. Unfortunately, eval is highly insecure and we're not going to allow ourselves to use it. So we're going to have to decide ahead of time when we're prompting the user for number values whether we're going to expect them to give us float or integer values. You'll notice here that even if I ask for a float 32, if they only give us the integer part, it's still going to work. We'll get a 32.0. Okay. So using it instead of eval ensures the user can only enter valid whole numbers. Illegal non-int inputs will cause the program to crash with an error message. One downside, this method does not accommodate simultaneous input. And what he means by simultaneous input is the flexibility that we would have been able to accept either ints or float of values and get eval to turn them into the right internal type. Now that was a nice thing that we were able to do in a non-threatening world a long time ago. That ship has just sailed. So we're using int and float to convert the strings that we get in with number values in them. Eval is just an insecure, hazy memory of the past. Okay, so now we're going to talk about type conversion and rounding, and we have a program here called change.py, okay? And this is where I typically bring in my version of these. I've taken these and I've opened up the code, right? So this is a program that it's a change counter. Please enter the count of each coin type. It's using eval for some reason. I don't know why we're still using eval. I think that's something they forgot to change. Because these are all counts, these should have been ints, right? And then we take the counts and we multiply to them times their fractional values in order to come up with a dollars float value. Okay, now this has quite a few problems that I've fixed in this change refactored. Okay, so let's look at this. I have, first of all, I've given you proper doc string. Okay. Second, we're prompting the user for the counts of quarters and dimes and nickels and pennies, but we're calling int because that's a secure way to take a number value typed at the console and turning into its internal int type. And then on line 12 here, where we do the calculation, I've added parentheses, even though they're not absolutely necessary. It's good programmer practice to include them, and that's what we're expected to do in my class. And then we're printing the answer. So here, if we run this refactored, it asks for each of the coin types. So I'm going to say we've got 4 quarters, that'll give us $1, 10 dimes, that'll give us $1, 20 nickels will give us $1, and 100 pennies will give us $1. And that the total value of our change is 4.0. That's perfect. It would have been nice if we were able to control the how many decimal points we had here, and we were able to point 4.00 because this is dollars and cents, but we haven't gotten to that in this part in the textbook. Okay, so that's what's going on there. Now, in addition to the math operators, okay, that are built in, including addition, subtraction, multiplication, float division, integer division, exponentiation. That's the modulo that gives you the remainder. And the absolute value is built in. Okay, we have a lot of other math functions that are available in a math library. So this may be the first library module or package that we're learning how to import and use in the Zelle text. Okay, math. Okay, so let's write a program to compute roots of a quadratic equation. This is not interesting to me. I mean, this is interesting to Zelle because he's a mathematician. This is sort of alienated to me and to my non-math oriented students. So I don't spend a lot of time on that. But let's say we wanted to write a program in which we wanted to use one of the functions in the math library. How would we do this? Well, up in the beginning of the program, after the doc string and before the main function, we have a line that just says import math. That means that we can now use any function within the math library with this kind of import. If you wanted to use square root, which is one of the things that he uses in that program that he's working up to, if we said import math, then when we wanted to use the square root function, we would say math.sqrt. We say that right here. Okay. Now, I'm just going to make that point without getting into the program. The quadratic program might be interesting. If you are interested in those things, I'll leave that to explore for you to explore on your own. Now, what functions are in the math library? Well, it's not only functions. Like we have some constants. We have pi. Okay, so it's an approximation of pi, so that's probably a float. Okay, we have E, which is also called Euler's number. Okay, that's E. And then we have a bunch of functions. Okay, and this is not exhaustive. So we have a bunch of trigonometric functions, and we've got square root. Okay. If we want to do exponentiation, and we don't want to do it with the built-in star operator, we can use math.exp. If we want to get the ceiling of a number, okay, or the floor, okay, this is something that we would do on a float in order to bring back a whole number int. Okay, what's the ceiling? Well, it's the int to the right on the number line. Okay, so if we had 4.5, right, then the the int to the right of 4.5 is 5. If we had minus 4.5, then the int to the right is 4. Floor is going to give us the int to the left of that float. So if we had a positive 4.5, then the floor of it is on the left. It's going to be 4. If we had a negative 4.5, then the floor is going to be on the left, on the number line. It's going to be negative 5. Now we've gotten away from quadratic equations and we've introduced the idea of factorial calculations. So you can take an integer and you can say you want the factorial of it. So if you want the factorial of 3, it's equal to 3 times 2 times 1. Well, of course, if you multiply by 1, you're just going to get the same thing. If you want the factorial of 6, it's going to be 6 times 5 times 4 times 3 times 2 times 1. And in this case, we have 6 exclamation. The exclamation is mathematical notation, not Python syntax, but mathematical notation for factorial. So 6 exclamation is 6 factorial. So what he wants to do here is he wants to show us, and we can write a program with looping that can calculate the factorial of any integer. Okay. And he shows us that we should expect if we were input a 6 to that program, when we write it, we will get the answer 720. And we'll see how that works. So how could we write a program to do this? Well, this is pseudo code. Input number to take the factorial of n, compute factorial of n. And I think he's saying here that he's going to use the variable n for the number, which is, I guess, okay. We're kind of doing math as match. And compute the factorial of n fact. Okay, why didn't he call it factorial? Well, because he ran out of room on the slide. Okay, this isn't a particularly good name. It's the one that fit with this big fat typeface. Okay. So how did we calculate 6 factorial? Well, we see how that worked in a looping kind of way. Okay, kind of doing it by hand. Okay. What's really going on? We're doing repeated multiplications and we're keeping track of a running product. This algorithm is known as an accumulator because we're keeping a running answer. And the variable that we do in it is called an accumulator variable. So at this point in the text, we're introducing another programming design pattern that would roughly be called accumulation. Okay, it's more typically done with addition and subtraction than it is with multiplication, and that's why I think this is a horrible example to choose. I would have chosen addition and subtraction. So the general form of an accumulator algorithm looks like this. Initialize the accumulator variable, loop until the final result is reached, update the value of the accumulator variable. So this indented update the value of the accumulator variable is the one statement in the body of this pseudocode loop. So it looks like we're going to use a loop. Okay, so fact equal 1. This is the name of his accumulator. Okay, I might have called it accumulator. Okay, now why 1? Well, it turns out that when you're doing this rare use of an accumulator for multiplication, the neutral value that you put in the neutral initial value for multiplication is 1. Why? Well, because any value times 1 is going to be equal to that value. Now, what if we were doing addition and subtraction? Would the initial value of the accumulator be 1? No, the neutral value for addition and subtraction accumulator is 0, because any number plus 0 is equal to that number. That's why I'm not too crazy that we're doing this in this example in the textbook and in the slides with multiplication. So he says for factor in 654321, okay, so this is a list of values that the index variable factor is going to take on. And then we say fact, it gets assigned fact plus factor. Okay, so fact is the accumulator. So you'll remember that the way these expressions work, the way these assignments worked, is we're saying this: the value of fact before we execute the statement times the value of factor before we execute this statement is going to be calculated, and then we're going to put the result into fact, and that's going to become the new value for fact. Okay, and he traces this through. So we say here, if you use fact without assigning it a value, what does Python do? Well, whenever we try to use a value in an expression and we haven't already initialized it, we're going to get an exception, and it's going to blow the program up. Since multiplication is associative and commutative, we can rewrite our program as this. And again, this is more of a math insight that I'm less excited about than the author is. Now, then he starts thinking, well, you know, that list I had for values, I could have expressed that as a range. Okay. So he shows us a new version where it's a range. And while we're at it, we go to the REPL, the Python console, and we say, hey, how can we use range to create the sequences that we want? Okay. And then how would we convert those to lists if we wanted to see them as a proper list? Well, we'd have a range expression inside of a call to list. Okay, range creates the sequence, but it's not formally a list. We'll learn when we get to chapter 5 some of the properties of a real list type. So range is a sequence, list is a sequence. They've got slightly different operations. So we're going to be a lot more familiar with lists than we are with ranges. So that's why we're converting it to a list. Okay, so if we just say range 10, convert that to a list, we get a list with 0 through 9. If we say that we want range 5, 10, well, this is going to say 5 is the first value that we want, and 10 is the first value that we don't want. That's one higher than the last one that we want. So what do we get? 5, 6, 7, 8, 9. Now, the way we express ourselves here, the mothers and fathers of Python like this. They did it intentionally. I find it very unattractive. We all have to live with it. And then we can also have an increment. So we can say range 5, 10, 2. So the start value 5 is the same. 10 as the first one that we don't want is the same, but 2 is how much we increment. So we go from 5 by 2 to 7 by 2 to 9. 11 would be past the first one we don't want. Okay, so this was our way to explore range a little bit more fully. And he wants to talk about how we could use range to do some interesting stuff. So we can count up from 2 to n. We can say range 2, n plus 1 will of course be the first one we don't want. So the last one in the range is going to be n. Do we have to use n plus 1? Yeah, we do have to use n plus 1 because, again, we're looking for the first one that we don't want. We can count down from n to 2, okay? So we have n. We're going to go down because increment is minus 1. Why don't we say 2? Well, when we're counting down, 1 is going to be the first one that we don't want. So let's say the n were 9. So we want 9, 8, 7, 6, 5, 4, 3, 2. 1 is the first one we don't want. So he shows us our completed factorial program. Okay. And again, I'll bring over the PyCharm version. And this is the code from the book. And again, the book has some problems in formatting. There are some formatting errors that violate the PEP8 style guide. And this is largely done to squeeze the code onto the printed page and onto the slide. And this is something that book authors and courseware developers do all the time. But it's not something that we're going to do in our class. Okay, so I've refactored this to make it less a program written by an academic book author and more a program that we might be expected to write on the job. So first of all, I converted the doc string. Okay, and one thing that we probably haven't talked about so far is that if doc strings have a lot to say, they say a summary on line 1. Okay, and I just want to point out there are several schools of how to formulate or how to compose a proper doc string. This is a very influential and popular one. Okay, so the first line has a summary, okay? It just has to fit on one line. The second line is blank, and then any other detail starts on the third line. So if we go back to this, he had 2 things to say in the comments. Program to compute a factorial of a number, illustrates for loop with an accumulator. And we're going to say the same thing in the refactored version, but the summary comment is up here. There's always a blank line in between, and then the detail comments begin on line 3. Okay. What else did we change? He used int. Okay. I put better spacing in here. Okay, I added a line between the end of main and the call to main. Okay, and we just generally cleaned it up. So if we run this factorial refactored, okay, and we give one of his example numbers like 6, well, it's going to get 720. Okay, so again, when you refactor a program, You don't change its functionality. It still gives the same answers, okay? What do? You improve its readability, testability, maintainability, and probably reusability or shareability would be yet one more thing. Now, I want to point out one kind of opportunity here that was lost. Remember how we talked about using the math library? Well, I didn't show you a whole lot of that because I wasn't keen on the program example. Well, here's a place where we can use it. So I've got a version here, Factorial refactored yet again. Okay, and it turns out that the math library includes a function called factorial. And you pass it an int, and you get back an int that has the factorial of the int that you passed in as a parameter. Okay, so what do you have to do to be able to use it? Well, first of all, you have to import math. Okay, and the examples in the book were just saying import math. If you say, let me change this. If you just say import math, then every time you use a function or a constant from the library, or I guess it could be a class when we get into later things, you have to prefix it with the namespace math. So you would have to say math.factorial. Okay, and that reads pretty well. All right. Now, as we learn more about imports, what we're going to find out is that when we import math, we import the entire library. Okay, and maybe that's not the most efficient thing to do. So there's another form of the import. There are 3 or 4 actually, and we're just going to examine the second. So we say from math import factorial. This is considered to be a good practice because we're saying just what we want to be loaded into the Python execution environment. Okay. And then when we use it, we can just use the name. Okay. What other improvements did I make? Well, I didn't call the variable for the factorial fact, or I didn't call it factor. If we're going to call the number n, which is kind of a mathy name, well, then I think we ought to call the factorial n factorial. And how do we get that? Well, we just call factorial and we pass n. Okay, and then we print it out essentially the same way. So let's look at this, run, and let's give it the value 6, and it's going to give us the same answer. Now, it's always a tension when you're teaching beginners between showing them how to calculate things by hand, which is what the factorial example from the book does, and equating them with the library packages like math, where you can just call a function to do it. In the long run, it's a better practice to import and call a library function because they're probably more efficient than your hand-coded version, and they get more efficient over time. They never get less efficient over time. So in new releases of the library, they never get worse, they only get better. Okay. And of course, if you hand code it, you have to design it, you have to code it, you have to test it, and you have to maintain it over the lifetime. If you use a function from one of the library modules, you have to you have to learn the library module. You have to learn how the function or whatever that you're going to use, how that works. Okay. Uh, you have to code it. And then when you're done, somebody else is doing the maintenance on that implementing code forever. Okay. So the author kind of emphasized doing this by hand because he wanted to show you some accumulation, but I showed you this because I wanted to show you how to do this with the factorial function from the math library. Now, what if we ask for the factorial of 100? So now let's just go back, look at our new kind of refactored version. Does it work for 100? Yeah, it does. And it gives us a really long answer. You see there's a slider bar down here. Okay, and it goes on for a long time. So 100 factorial is really big. And this is one of the ways he introduces the idea that the Python int type is not limited in its number of digits. The number of digits that a number has is, in computer science terms, is called its precision, and the number of decimal digits is called its scale. So floats have both precision and scale, and ints have just precision. Okay, and modern Python, which is Python 3.0 and above, have ints with unlimited precision. Now, newer versions of Python can handle it, but so he's showing Python 1 or even Python 2. I just want to drive a nail through the coffin of any Python version earlier than Python 3. The Python Foundation, who's responsible for the guidance of Python, called time on Python 1 and 2 on what's the sunset date? January 1st, 2020. Okay, so Python 1 and Python 2 are no longer supported, only Python 3. So we shouldn't be talking about Python 2. We shouldn't be using Python 2. We shouldn't be reading books that are about Python 2 unless we're a programming historian. Python 3 is it. So it turns out that the computers, the CPUs that are in the computers that we use, they don't actually have computing hardware that can add or subtract or multiply or divide integers that are infinitely long. Okay? And how big of an integer they can do math on really has to do with just the architecture of the computer. Is it a 16-bit, 32-bit, 64-bit, 128-bit processor? Okay. Now, Python, under the covers, will do the computing to make sure that any math operations on big int values are done properly, well, it has a function that expresses how to do the math on large ints in terms of the things that the processors can actually do. Do we need to worry about that? I'm going to say no. Okay, what about float types? Okay, is there some point, if we have a very large int value, would we want to represent it as a float? The problem is that floats only hold so much precision. So they can represent a very large value because they do it by kind of scientific notation. Okay, so so we have a value, okay, and then we have an exponent, right? This allows us to represent very small and very large values, but their approximation. Okay, so large ints, let Python have its way with large ints. Floats do have the problem that they have approximation errors. They come from two sources. Source number one has to do, they only keep so many digits of precision. Okay. And the digits of precision are, I may have misspoke a few minutes ago. Precision is all the digits that they keep. So they keep about this many digits, right, for a float. And the scale is how many of them are to the right of the decimal point. So when you think about ints in terms of precision, well, they have infinite precision because we can have all the digits that we want. They have a scale of 0 because they have 0 to the right of the decimal point. So the second reason that we get approximation errors in floats is that under the covers, these are converted to binary. Okay, and binary fractions are slightly approximationally different than decimal fractions, and so we'll get some situations where we're expecting to get a very neat value, like say 1.7, and instead we'll see 1.699999992. Okay. That's a very small difference. So I typically say that with floats, they're accurate enough to get a rocket ship to Mars, even with the rounding and approximation errors, but they're pretty thorny for getting your checkbook to balance if you've got really large amounts of money, like a very wealthy person would have, or a bank would have, those kinds of things. Okay. So here again, I forgot we had this slide here. So that notation for the float, again, is using the scientific or exponential notation. So it's this value times 10 to the 32nd. Okay. And again, that's a great way to express a value if you're doing even engineering. Okay. But sometimes if you're trying to get exact pennies, it can be challenging. So floats are approximation. Floats allows to represent a larger range of values but with fixed precision. That means we're only keeping so many digits. Python has a solution for ints. It's just the big ints, you know? They have these very flexible expanding ints, and the Python interpreter takes care of whether a particular value could still be done with the basic built-in math of the processor that we're running on, or whether we have to start to run some sort of implementing algorithm to do the math on these things, because they can't be manipulated by the processor that we're running on. Again, in Python 3, it's not a thing that certainly a beginner programmer would ever want to worry about. Newer versions of Python read real Python, Python 3, automatically convert your ints to expanded form when they grow so large as to overflow what would work on that processor. And again, not all processors have the same word length. Old processors, old microprocessors for PCs had some of them, I think, were even 8-bit processors. Then we had 16-bit, then 32, then 64. Some were 128. Okay, but not for us to worry. And that is it. Okay, so that's all. I'm gonna wrap up here and say bye until next time. Bye bye.